My name is Boros, and I'm presenting with Károly Nagy. And we will talk about the automation that we are using in Dropbox for Dropbox databases. So how do we automate things? But first, before talking about that, we want to share a few things about our team and about Dropbox. So our team is globally distributed. We have members in Dublin. This is not Dublin, California, but Dublin, Ireland. San Francisco, Seattle, and Malta. This is not Malta, California, but Malta, Malta. And as many of you know, Dropbox is about file synchronization and sharing. Who doesn't know what Dropbox is? Okay, so we will skip this part. But a bit about numbers, like about what we have built. Dropbox has 500 million users, 200,000 businesses are using Dropbox for business, and 1.2 billion files are saved on Dropbox every day. Our team is responsible for the databases, which is providing the metadata services for this. So whatever file metadata you have ends up in a system we manage, at least in the lowest layer. So we have three biggest databases. We have a database called Server File Journal, which has the file system metadata. We have EdgeStore, which is a more general purpose graph database, and we have metadata databases for Magic Pocket. Magic Pocket is our storage system, which stores the actual data, but we even have metadata for the actual data. And we have tens of smaller other databases which every company has, like various. You can imagine that as a company grows, it will grow various databases as well. And we are managing those various databases, and those are MySQL as well. So if you want to learn more about EdgeStore, there is a talk about it yesterday. So, and we will talk about how are we doing operations. And we rely heavily on automation because this counter never moves from zero. Like, who says a master failure is scary in their environment, or a master promotion is like not every day. So we don't have that luxury to allow us for that to be scary. So there is at least one master failure every single day, and Dropbox is not down every day, so automation, generally speaking, works. And now I hand over to Károly.
Yeah. So in order to keep yourself sane, it's important to automate all your stuff, right? And before we go to automation, let's talk about what is automation, because it's not just one magic word. Because there are multiple levels of automation that you can write and you have, and many of the companies have all sorts of level of automation, and let's just go through them. So where you start is always scripting, right? That's easy. You basically make the computer do whatever you would do as sitting in front of your computer. Just write a bash script or a Python script, Go, whatever you like, and you do make the computer do the very same steps that you would do. That's why the nice image with the training of the dog. It's pretty much what it is. It's very good. Very easy to start, but reliability is sort of limited, and you want to move on to this because you're still SSHing into the box, you're still doing stuff manually, but it's just more convenient. So there's a scripting plus where you execute these scripts remotely, you execute these scripts parallel, whatever you wish, and you can do this on multiple hosts. So where high you're growing, your fleet is growing, you get better at doing multiple stuff at the same time. Very good example of this as framework is Ansible, where the very same task runs on probably hundreds of machines, for example. But you can still go further than that, and you can run scripts without you being in front of the computer, maybe watch your favorite series, whatever, and the computer do the job in the back end. You can do this with Chef, Puppet, Salt, the cron job can run. And that's basically what it does is you have a list of things that has to be that certain way. And all of the other config management systems are all about that you make a system look as a certain way as it is described, and it will do it very well for you in the back end. Still, it won't take care of promotions, because how are you going to tell Salt or Puppet or Chef that that master died? What you really want to have is a self-managing server infrastructure where your servers can react, so you can focus on the important stuff, right? Playing is important. You can do this several ways. One way is that, as mentioned, reactive, and you can also schedule this. You can have reactors, so you can read data from Graphite, your monitoring system, Nagios, whatever, and then react on that. But how you do this on thousands of servers, that's an interesting question, because there are many things that can go wrong. So why not use Chef, Puppet, or Ansible? Because these are awesome stuff for, as I said before, config management, doing the same thing over and over on many, many hosts. Awesome for that. Not so very good when you want to synchronize these jobs. Who knows how promotion works in MySQL? I was expecting a bit more hands, but all right. So you don't do the same job on the master and the slave, right? It's not the same script running on two machines. You need to synchronize. You need to change masters on the rest of the slaves. So there are multiple things that you need to check and making decisions. Which slave are you going to promote? That's not always an easy answer. Puppet, Chef, Ansible cannot answer that for you. So, a couple of things. You run into a scalability issue. And I'm not talking about scalability because we are all large IT companies, we have money, we can buy servers. But there is another complexity. What you pay as an engineer is the complexity of the program you're writing. The more servers you have, the more automation you have, it's an exponential problem to make it sure that a centralized server can handle all of this. And you will run into this if-else nightmare where you're writing conditions. If there is a clone job running, don't run a backup. If there is a backup running, don't run a promote job. If there is a promote job running, don't do whatever. You can see where it goes. And when you have thousands of servers, it's you cannot manage it. You cannot go to that point. Orchestrator challenges. There are very long-running tasks. You need to control parallelism. You need to get data. When you do a promotion, you need to know where each slave's at replication, which GTID did they execute last time, how far they are from the master. These are the low latency query type that you need to get quickly. Again, Puppet, Chef, Ansible cannot answer that for you. And the biggest issue with those long-running jobs. Okay, GIF is working. Most of the database jobs are slow. Databases are slow. You cannot clone a 2 terabyte database in a second. And even after half an hour, how Chef or Puppet runs every half an hour, it just won't work. You cannot run it in the background. At Booking, we had the very first try of cloning, we had a Puppet job starting a clone with a nice sign at the end of the script, put it in the background. We realized it quickly that whenever you run Puppet, you will start a clone job and you will kill your box pretty quickly. It's a very hard thing to manage. So we came up with a list of things that we want our automation to be good at. We're not trying to replace these stuff because these are meant to be configuration manager, they're good at. We just want something that works best for us, which is locally relevant information is locally available. You don't need a centralized point for that. Bias to local decisions versus centralized decisions. So whatever you can decide on a host level, decide on the host level. If you need to go to the cluster level, decide on the cluster level. You don't need to go outside of your scope. states and atomic transitions between them. A promotion shouldn't leave your master and slave in a weird state if it fails. Modular architecture, independent reactive behavior. We do not want to work. We are lazy. And we want a constant complexity because we are growing. We don't want our system to be growing the same time or even exponentially with our growth rate. So, we came up with, So we came up with this system, and we broke it down to 4 pieces. One is the config management. We have a state machine. We have a framework that moves infrastructure between these states, and we have an agent which acts on every single server we have and can run different things that we wish for.
Okay, so first part of this, what we built is configuration management. And we built our configuration management part with Python and Jinja too. So how the configuration management works is that it provides us hierarchical templatable overrides. So we have a master configuration. Imagine that this is like a bunch of JSON files somewhere, right, which describes the configuration of the entire fleet. And based on this central configuration, each node can assemble its own configuration without talking to anybody else. And this configuration is pretty much static. And this is how you can use it with Python. So, for example, here we imported the getInstanceConfig method. We are creating a configuration for the instance, and it has an overrides method. So you can check what overrides did that particular configuration pull to itself. For example, and this has a directory structure. We are naming our machines after wrestlers. So the hardware class configuration it will pull in will be virtual.json. This means that we pull in the hardware-specific configuration for that specific machine type, which has a number of disks, and whatever amount of memory, whatever CPU, and all the configuration related to this is in that override. Also, that instance we created here is a slave, so it pulls in the slave override as well. If it's a slave, probably it's running with read only equals 1, and so on and so forth. So you have a slave specific. And then we have a category override, which describes the machine in the service discovery. So, for example, if this is an edge store node, or this is some random database for finance, or what kind of database is this? And so it pulls in a base configuration. It does the overrides based on the overrides it pulled in. And the overrides can go as deep as you want. You can create an override based on any property of service discovery in our infrastructure and any property in the machine management. Like we have a very similar, so if you know AWS, they have tagging and attributes. We have a very similar functionality for physical machines, and you can override configuration based on any tag or any attribute. For example, if I want to canary a new MySQL version, I would just create a MySQL 5726 tag and put it on some machines, and they will pull in an override which will override the MySQL version that we want to run. So we are using this for MySQL configuration, and MySQL configuration is pretty simple. Like we set the backlog to 1024 like this. We set the base there like this. So it's a one-to-one mapping of the my.cnf itself. What is special about our configuration management is that we have also a configuration part which describes what parameters do we want to set statically and dynamically. So it knows about the MySQL specifics. Like it knows about that if this parameter changed, I can just go ahead and do a set global. If this parameter changed though, it needs a restart. And the instance will be in a state that it will want to restart itself. We are also storing database users in this type of configuration, like what users do we want to have on the database. For example, we have different users, on different databases. So the description of that is there as well. And we have all the instance-related services in this configuration. For example, for each instance, we are running PT stalk. It's a pretty good idea to run PT stalk for each instance. For each master, though, we are running PT table checksum to make sure that we have data integrity. Like, for example, the PT stalk override is in the base config because we want to run it everywhere. The PT table checksum service, though, is in the master override because we only want to run it on masters, right? And here is an example of the configuration itself being templatable. So to each of these configurations, we are passing the object that generates that configuration, and it can call out to other objects. For example, this configuration is handled by the service object. The service object has a backlink to the instance configuration, so I can get the MySQL socket from the instance configuration, which will be passed to PT stalk as a command line argument, right? So you can see that this is really, really flexible. Like all the levels are, all the various levels are accessible from all the other levels, and you can use them in the templates as well. And so this handles configuration of a single thing, which is static in time. But database nodes are not static in time, right? We have machines which are in the free pool, or what we call free pool. And these machines are in free state. In free state, they are not running any database. They are just ready for usage. Also, we have non-production slaves. Like, in order to transition something from a free state to a non-production slave, we have to make a clone of something, right? This transition takes several hours, or can take several hours if the data set is big enough. Then we have a state called production slave when it's added to service discovery, and customers of us are actually allowed to connect to it. And we have masters, which if you promote a slave, it becomes master. And each of these states can be described with the configuration mechanism that I just described. But let's say I want to make a new clone and I want to transition from free to non-production slave. How we solve this is that we have factories called transitions, so factories are taking an instance configuration and they are emitting instance configuration of the next desired state, or configuration of the next desired state. So whenever, for example, I have a clone or bootstrap operation, bootstrap is creating new database, then I can just grab a free node, create its config, create this transition class, and create the new config, which reflects the state when the clone, which the node would be in when the clone is completed already. So I have access to both this state metadata and this state's metadata. And these objects here are immutable. These transition objects are factories, and the ones in squares are the operations that are using these transition objects and configuration objects. here is an example for transitions. For example, I create a slave to master transition on the instance config I created previously. Then I call create instance config method. So I can have, at that point, I can have access to the metadata of the previous state or the current state and the next state, right? So in the next state metadata, it's already described that this next state is a master, but at this point, it's just metadata, right? So I know what the master will look like later. For example, here, if I check what user should I add when the node is slave, I get back that I shouldn't add any users because the node is already or the instance is already in a good state. But if I do the same, if I get the same data for the transitioned class, here I will get that I need to add the writer user, okay? Because we are dropping so we only have a limited set of database users on every database, and whatever is not in use or doesn't make sense to use, we are just dropping them in the transitions. So what this gives us is very easy rollbacks supported by the framework, because in all the operations we have access both to the next state and to the previous state. So how do we use these easy rollbacks with transitions? For example, this first example is from the promotion code, right? What the framework gives us is that if this one fails, which is I want to apply all the ACL changes on the new master, and I can define the negative operation right away, which is push to a stack, which is, do the same thing but on the slave object. So this negative operation is pushed onto the stack, and whenever there is an unquote exception, the rollback stack is executed. So this is what gives us like no half-done things. Who had an MHA failure before, or something like that, like half-done master switch, right? Then you have to like go ahead and revert manually. It's quite tedious. You have to know your master switching framework really well. And what we did, we practically never have a half-done promotion with this, or a half-done master switch. And it works with everything. Like, for example, this sets read-only on the new master and backs it, and the inverse operation is backing it out. Sets read-only on the new master based on the configuration of read-only on the new master, right? Which is most likely 0. And the inverse operation is setting read-only on the candidate master, which comes from the configuration of read-only on the candidate master. And now back to Károly.
So Peter mentioned framework, so introducing drops, which is short for Dropbox Operation Framework, which is what is a easy way, declarative way to write very complex operations in a very pluggable fashion. Supports rollback ability, reversible also, and traceable. I want to mention reversibility and rollback is not the same thing, right? Reversibility is when you can reverse an already done operation, and rollback when you roll back a half-done operation. That's why later on it's important to make that difference. So why do we need something like this? Because as you probably know, most of your operation that you do on a database looks the very same way, right? What is the first thing you do when you start a promotion? So, tip, you check if you can do it, right? You check if you really, what you want to promote is a slave, and the master that you want to demote is really a master, because you don't want to run a promotion on a slave down the stream somewhere deep. You check if the hosts are accessible. You check if you can actually proceed with the operation without any issue. Then you do some preparation. You regroup the slaves. Then you do the actual promotion, and there are some jobs at the end, cleanup jobs. You may need to change configuration. You may need to move slaves back around or whatever. So all of these are always the same. Every single operation. Cloning is the same. Adding something to the production is the same. You always want to check, do some work, finish the work, and clean up if it didn't succeed. And sometimes you want to run parallel, sometimes you want to run sequentially. It really depends on your work, how you want to execute it. But we always want to stop if it fails. So we thought, why would we write this all over and over and over again for every single operation? So that's why we came up with this. We created some basic modules that we use. So we have operations, short op. We have stages, we have pipes, we have pipelines, and we have a Fanout, which we call Fanout. Now I just saw Max arriving. No? I thought I was just seeing Max arrive. So that was a very interesting name we came up with. We were discussing like 50 different names. This is the best one we came up with. If you have any better, then please let us know. But this is the current name for the Fanout. And it's built around data pipeline. Something moves through a pipeline, and your data is going through. So each operation will give input to the next operation, which will give input to the next operation. So it's very much like a pipe in shell, because I know many people like shell. Many people can write very nice one-liners. Brian had a nice talk about that. So people know Bash, people know pipelines, and we wanted to sort of get this idea into a larger complexity, larger scale. So what are operations? Operations are the workhorses of the framework. Operations are the smallest unit, and it's basically everything that changes anything on a database. If you just change a parameter which has an effect, like asynchronous replications, you change the semi-sync, it's an operation. But also cloning is an operation. Promote is an operation. Changing attribute in our inventory system is an operation because it has an effect. Whatever has an effect on the system, it is being executed with an operation. It has reverse operation. What makes sense, of course, not everything can have a reverse operation, but everything has a negative operation which does exactly the opposite of what this operation did. For example, promotion has a demotion. Add to prod has a remove from prod, and so on. Runtime behavior parameters are all logged, and we know everything. So every operation is timed. Every operation is logged. We can put it in centralized logging. We can put it into Hadoop or Elasticsearch for later trace or debugging or whatever you want. And it has a runtime that executes on. It's important because what you do is every operation is a class itself in Python, and when you instantiate, you create an executable. So from that point on, it works as a function. It's an internal behavior, but it makes things like this easy. So last week I just wrote an S3 backup, and it literally took that amount of code. Why? Because we already had the push-in instance, and you just need a parameter where to push, instantiate, you get a function, and then you can execute. Then you have a get S3 pusher, which pushes a database to an S3, and then you have a backup script. The same thing for cloning, right? We have the push instance, we just need to change where we push it to. It has a bit of an extra bit because you need to receive it. On the other hand, but that's also handled because we can build complex pipelines, as I will show a bit later. So backing up an instance is just that 4 lines and calling that function with that 1 line. That's the power that gives us. So we cannot spend our time always rewriting the stuff. We can easily create operations like that. Pipe and stage, I talk about them together because roughly it's the same. They help each other out. Pipe is something that changes something on the pipeline, like data manipulation. Because many times stages don't want all of the data that the pipe contains, or they want some format that is not matching. So we have this pipe, if you know Amazon, Lambda functions, roughly the same as pipe. So something comes in, something gets out really easy. And usually we write Lambda, actual Python Lambda functions in pipes. Stage executes one type of operation on many things. Whatever iterables you can come up with, list, dictionary, tuple, any type of iterable objects, the stage will execute the operation that you instantiated this stage with on all over. And how you want to run it, sequentially, parallel, or 3 at a time, 2 at a time, it's completely up to you. It's configurable. Stops on failure. And what this can do, and this is why I said reversibility is important, because if you have like 8 jobs, I think you didn't mention multi-instance.
Yes.
So we run multiple instances on a single host, multiple MySQL. So for example, if we run a promotion, it means that we have to, let's say, promote 8 MySQL instance on a single server. And so we go through, iterate over the 8 boxes, and if 5th one fails, we reverse 4, roll back the 5th, and don't do the rest. Fanout is when you need more. It's basically like a in shell. You move it to multiple, so your pipe moves to multiple places, and you can do multiple pipelines after that. So this is how a pipeline looks like. That's what you can configure. You have stages. This is the stages, and this is the fanout. And then your job executed and it ended. So this is how your data goes through. Let's say you have a node coming in, that the node failed, you need to promote. It goes through and do all the job that is necessary, and then you will get the end result. This is the promotion code for a whole node that can contain as many instances you want. And again, you can see this is a very easy configurable way. You don't actually write Python code, you write mostly configuration. And you can build up really complex stuff. We wanted to come up with a nicer pipeline that is very complex, but literally, because we have this fanout and sublines, a pipeline can be an operation, a pipeline can be a subline, and you can just build whatever you want from this at this point. We also have local agents. What this does is we have multiple smaller agents that can do small iterative stuff, like every 5 seconds, every 10 seconds, every second, collect some data. Performance metrics, health metrics, user grants, so on and so forth. They create an event. They put that event onto an event bus, and we have a dispatcher that dispatches that events to certain reactors. Reactors can subscribe to events, and they do stuff with it. So, for example, monitoring script can be an agent and the reactor. Agent collects data, reactors puts it to, let's say, graphite. But you can also put it to HDFS at the same time. And this is exactly the benefit why we're doing this, because you decouple the two different behavior. One is a collection part, one is a action item. And you don't combine these two together. You can easily replace parts. We have some older scripts, legacy script that we need to maintain. So we can have a collector, and we can have multiple writers which writes to new monitoring system, legacy monitoring system, whatever we want, and just not do anything with it. It's really easy. For example, these are the agents that we have right now. We have health, performance, replication, process list, and heartbeat. This is what we are running at the moment. And these are the reactors we have at the moment. Monitoring writer, which writes to the monitoring system. Local cluster health writer, which writes to the local master. So every local information is available at the local cluster level. We have a query killer. So it reads from the process list, obviously. So it gets the process list event. And based on the payload, it can stop select queries. We have the instance pusher and receiver. These are for cloning, backup. And the failover is something that we're currently working on to have a local decision failover. And an example, this is the payload that would come from the process list event. There is a select query coming from a nice IP address, 192.56.9.1.1. And then there is this reactor which checks if all of the checks are valid. So it starts with a select. It is larger than what we specify as a threshold for killing it. If it matches a user, regex. If it matches a info, regex. And these are all coming from our configuration system. So you can override this the same way how Peter described it. So all good and nice, but everything can fail. So
one of the key things which allowed us to develop this is easy integration testing. So we actually have something reproduced in a single container which is extremely similar to the Dropbox production infrastructure. So with the push of a button, you can create an environment where you can do everything, break it, fix it, whatever. And this also can run automated tests. Like if we modify the promotion code, it gets tested in continuous integration in a way that it does an actual promotion and checks if things are looking good at the end. So this was really a key part to do it. Also, we are hiring if you want to work on this kind of stuff. And that's it.
Any questions?
I'll let you answer that.
No, the short answer is no. The long answer is technically you can make Ansible to run scripts, but that wouldn't be Ansible anymore. So if you would make scripts, most of the things that you cannot do with Ansible is retrieving information from others. So Ansible runs independently on every single host. Whereas what you want from a cloning or a promotion is to have interaction between the nodes. And you don't run the same thing. So Ansible runs a playbook. And Ansible runs a playbook. You can have when conditions, but that when conditions still run. That's something that I found out the hard way, is that every single task that you have in Ansible is going to be checked and executed, even if you have a when on it. So if you have a large playbook which has a lot of branching, your playbook is going to be very, very slow. So synchronizing between hosts, you cannot do right in Ansible at all. And Puppet and Chef were just not meant to do this because they are not running at the same time.
There is one more thing to it. Like when we were in the discussion if we should use Puppet, Chef, or write our own, with the state transitions, when we are generating the new configuration, like if you run Puppet or Chef or Ansible, how long does it take to, you change it and change your template, run the agent, like how long does it take, right? It's at least seconds. So in the config change, in the operations, the config change operations, what we are using is taking the double-digit milliseconds mostly. So there is also a performance consideration.
Anything else? Yep.
Is this something that's open or within Dropbox?
So right now it's very coupled to Dropbox infrastructure, like Dropbox Service Discovery, Dropbox everything. The framework is something which we could possibly open source. We don't know if there is interest for it. Yeah, if there is, at some point we can decouple it from the Dropbox specific stuff and maybe working on open sourcing it, but we figured first we will talk about it if it's interesting at all for other people as well, and if it's worth doing it, right? Yeah?
Yep.
Sometimes for maintenance tasks, I find I need to turn off query killer. Is that something possible with this infrastructure?
Yes. So query killer is just a reactor which reads config, right? So you can so turn off the query killer that you can either turn it off on the global config, or let's say you are experimenting something like, okay, something was fixed and you want to see it on a couple of shards if it worked, right? So you can create a turn off query killer tag or turn off query killer override, which turns off the query killer, which overrides at the bottom of the override stack. And then on the stuff which you canary the query killer turn off on, it won't kill queries. And when you are confident with moving it to global configuration, you just move it to global configuration. So we are using this for canarying stuff as well.
Other questions? No? We are here until 5:30, so if you happen to have any questions, we will be around. Yeah. Thank you.
Thanks.